I'll probably end chapter 3 completely in class tomorrow. Chapter 3 will be gone. And I'll start chapter 4. And probably tomorrow. And they continue with that on Wednesday, Thursday. Thursday, more than likely, have a chance to start chapter 5, which is the trig. And that trig's going to take a little time, though. So it's going to take me into next week, which will be our fourth week, to get into the trig and have some time to talk about the trig. Probably will take me all week next week, just do those 3 chapters on trig. Okay, then the 5th week, we're supposed to move into chapter 11 and do some sequences, and also touch upon chapter 9. That's the 5th week. 6th week, hopefully, I'll have some time left over during that last week to go back and recap things. You guys are moving fast. You guys who are coming at 2 o'clock, that's a salvation. Oh my goodness, and the questions the students ask, and you guys who are not attending for some reason, you don't get to hear those questions students are asking. Like they were asking about polynomial functions today and things like that. If you're not there, you don't get to hear that conversation from 2 to 2:30. Okay? So if you get there, please be there. Wednesday, I would expect a big group to be there. Friday, I would expect the hallways to be congested at 2 o'clock. Congested Friday to get ready for that test. Okay? Do a count here to see who's today. Missing some students. Okay, guys, here's what I will do with you. I haven't seen you for a while. Hope you enjoyed the break. Quiz coming up on Wednesday. So I thought, whoa, I better slow down, do a little recap here, not get too involved in this recap, and then move further into, let me check and see what all I did do here. I did. Finding the complex zeros of a polynomial function. Now, my 2 o'clock session, they're doing their homework. I know them, I'm beginning to get to know those students who are with me at 2 o'clock. Others, I don't know yet. I've just done one homework check, I think, with you guys. I'll have no clue until Friday until I look at your homework and see if you are attempting the homework. For goodness sakes, to take the class and not attempt the homework would be scary. Completely scary. So do try the homework. Don't just depend upon the notes and so forth. Now, I did this for you. This, I don't think you guys have this yet. It's two-sided, and yes, talks about complex zeros, how to find the complex zero, and also some rules maybe I have not discussed yet. And so we'll go through this and see what this is about. And this is a big part of chapter 3 done. Done. And then Mr. Park's making copies for us to close down chapter 3. Maybe I'll get a chance to start that today. Arena, can you do me a favor? Pass them out on. Guys, before I jump into this, I'm excited about this. 2 o'clock session had lots of questions to ask me about this. Does anyone have a couple? Anyone else? Okay, here we go. One side says section 3.3, and I think the back goes into 3.4. And that's a major part of chapter 3. If I can get through this and you make some sense of it, the big part of chapter 3 is done. And when Mr. Park gets back with the other copies, we'll start the ending of chapter 3. Guys, but I gotta be careful, because you have all this to worry about on the exam on Friday and a little bit on Wednesday. I'll tell you more about that quiz on Wednesday coming up. Okay, here's what I need to do. First, a colleague of mine came in. He's not teaching this summer. he came in to do something in his office, the first question he was asking, Randy, do you have any good students to send to me? He's teaching math 7. I don't know yet. I've just given one exam. I can't tell just from one exam. Because I've seen in the past, some students mess up on the first exam for some reason or the other, and all of a sudden they jump up, and jump up, and jump up. And one of my and can turn out to be one of my strongest students. So no, I can't suggest students to professor. That's what we're doing in math 7. Guys, section 3.3. We'll start with that side there. It says section 3.3. I need a student. Here goes, guys. I know some detail there. I really need to get down to what is Descartes' rule of signs. Before I jump into it, before I jump into it, you go. I need a student volunteer just to read up there at the very top. It says the real zeros of a polynomial function can be difficult. I need a student volunteer to just read that part, just to set this up. Any volunteers? Okay, Aiden, go for it.
The real zeros of a polynomial function can be difficult to find using algebraic methods.
Stop there. Definitely. If you're doing your homework, you know they can be difficult to find. And sometimes it can be so frustrating you just give up. Which you can't do it. I couldn't do it, but sometimes the way they're presented, you're looking for 8 zeros. Some of these things go up to 10 zeros, 12 zeros. And you can't even find the first one, or at least one. That's the problem, so he's right. Aiden, continue there.
No nice formulas like the quadratic formula are available to help find the zeros for polynomials of degree 3 or higher.
Now, I wish there was a formula out there, like quadratic for quadratics. I wish there was a cubic formula, a quartic formula, a quintic formula that would apply. Maybe in grad school, maybe they've discovered something like that. I don't know. But right now, we don't have that.
I don't know, it exists, but it's like really long.
Well, it could be, yeah, exactly. Now, Aiden, before I ask you to read more, just mention to the class remainder theorem, factor theorem.
Suppose f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. As for the factor theorem, suppose f is a polynomial function. Then x minus c is a factor of f of x if and only if f of c is equal to 0.
Now, the factor theorem says, like the synthetic, when you start checking, guessing at what the answer might be, what one of the zeros might be, what are you supposed to get on the end of that synthetic? If it works, you're supposed to get a what? 0. That's in essence what the factor theorem says. You're supposed to get a 0. I want to show you tonight, though, if you don't get a 0, there's also another benefit. Even if you don't get a 0, there's a benefit. So I'll talk about that tonight myself. They didn't mention it here. Read number 3 for us.
Number of real zeros. A polynomial function cannot have more real zeros than its degree.
Well, that makes sense. If the degree is 4, you're going to get 4 zeros. So not going to be 5. Okay, if you see a 10 on the exam, if you expect them 10 zeros, yeah, you're going to get 10 zeros. Then you're going to get 11. So that's the max that you can get. In fact, you will get that many zeros. Now, it all comes down to number 4. Oh my goodness, Miriam, I thought about you when I saw this handout. She's been doing her work in chapter 3, and she's been asking questions about professor to solve and find these zeros. We need as much help as we can. Aiden says they're not easy to find. Algebraically, from a statement he read, I agree 100%. So I need first to do this. Descartes' rule, great philosopher, also a great mathematician. And this is a rule that we have carried through math that he worked with, and we'll use it. Now, the statement's on your handout. There's no need for me to write the statement. Miriam, would you read the statement to the class?
For Descartes' rule of signs.
Uh-huh.
Suppose f is a polynomial function written in standard form. The number of positive real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer.
Oh, Lord. You open up a math textbook and you don't have a professor here, and you got to try to decipher, make some sense of, translate what she has read, translate that statement. So, Professor, I've done. I can understand the reading. Math is difficult to read, very difficult. Miriam, read that same statement to me one more time as I place an example on the board.
Okay. The number of positive real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer.
Here goes, guys. I think I have an example there on your handout. I think that's copied out correctly. Make sure it is. Okay, it says discuss the real zeros using what Miriam just read to me. Now, doesn't say find. Discuss. How many zeros am I expecting? 7. I do see some terms are missing. I would think, I see an x to the 7th. I would think, well, where's the x to the 6th term? Where's the x to the 5th term? Sometimes terms are missing. Here, though, with what they gave you, Miriam translates this. Descartes' rule says, before you try to attempt to find the zeros, which we're not going to find them here, look at the polynomial function and look from term to term for sign changes. Like from the first term to the second term, in my case, it changes from a positive 3 coefficient to a negative 4. Is that a sign change? From positive to a negative. I'll check that. From this term to this term, I'm going from a negative 4 to a positive 3. It changes in sign again. From this term to this term, there's no sign change. And from the next term to the next, there's a sign change. And from this term to the last one, a negative and a negative, there's no sign change. So how many sign changes do I see here? 3. The rule says that of those 7 zeros you're expecting, 3 of them might be positive, which might help you. But Miriam, I think they added something at the end which could be a little confusing. Okay, so right now I see 3 side changes, which says you might expect of the 7 zeros, 3 to be positive. And these are real zeros. Now the confusing part is she's going to read or. What do they add on the end?
Or else equals that number less an even integer.
Got it. They said, oh, this is another possibility. You know how formulas and rules are. Take that number, and we'll translate like this, and subtract an even number, unlike 2, which is a small even number, a positive even number. Just subtract 2 from that, and also consider it might be only 1 out of the 7 that are positive. Will be positive. And that's it. So of the 7, what could happen? 3 could be positive, and the other 4 could be negative. Or 1 could be positive, and the other 6 could be negative. Or someone add something else. Or what? Well, I'm talking about real zeros. That would be the possibility. I was supposed to write complex. This is for real zeros. Now, Miriam, tell the class, my goodness, how do I find the possible number of negative real zeros of those 7?
Okay, the number of negative real zeros of f either equals the number of variations in the sign of non-zero coefficients of f of negative x.
Oh, hang on. Do the same thing I just did with this one, but now first express p of a negative x. And then I'll repeat this routine. Hey guys, p of a negative x says please go through and replace those x's by negative. And be very careful when you try to simplify all this. This is cubed, squared, negative x here. Got to make sure I'm on top of the board here. I went through and replaced all the x's with a negative x. She says that's the second part of Descartes' rule of signs. Simplified, this actually becomes a negative. Be careful here, that's a negative 4x to the fourth. Be careful here, that's a negative 3x cubed. This becomes a positive, looks like 2x squared, positive x, subtract 3. See if you guys will agree. Did I simplify those terms correctly? Anyone follow me there? Did I simplify them correctly? If I did, let's hope all that simplification is correct. If I did, you go through the same routine. You go from term to term looking for sign changes. There's none there. From first term to second term. Second term to the third term, no sign change. This term to this, sign change. From here to here, no sign change. From here to the last one, there's a sign change. Is that true? So it says, of the 7 zeros, how many negative real zeros might I have? How many sign changes did I end up with here? What was it, 2? So I could end up with 2 negative real zeros. And then I think they add on the end there, Miriam, if I'm correct, what was that ending remark they made?
Or else equals that number less than even.
Okay, take that number and then subtract 2 from it. He calls it an even number. I'm using 2. Therefore, if I do it here, there may be none. That are negative. Now, will this help at times? It will help at times. It will help you at times. If you just slow down and see how many positive real zeros you might expect, how many negative real zeros you might expect, and therefore you move on and try to find your zeros. Now, I don't think I have, did I have any examples on the handout? Or is this one I have on the board? Is that the only one I have?
On the board.
Is that one? Was that
Yeah.
it? Okay, now, let me point something out, and I'll get some questions here. If, here's a benefit. If I should ask you, here goes, to find, I'm just making this up, guys, stand here. There's your function, you're expecting 3 zeros. And then of course you start listening to P over Q, rational zeros theorem, you start testing by synthetic, hoping for an answer. And though you may say, oh, I'm gonna slow down and see if Descartes' rule would help me before I start off my business here. Guys, how many side changes do you see as you move from term to term here? None. There are no sign changes, which tells me of those 3 zeros I'm expecting, how many can be positive real zeros? None. So in your possibilities, you'll get some probably positive possibilities to test. Don't test them. So when you start looking at all your possibilities, you start testing by synthetic to see what works. If that should work out there, avoid all the positives. There is no positive real zero there. And you can do the same thing on the negatives. Okay, there may be no negatives to worry about. Okay. Miriam, is that all I had for that there on the handout?
Yeah, the next
For
one.
Descartes' rule, I mean for Descartes'
Yeah.
rule. Now, guys, here we go. Oh my goodness. I need another volunteer to read number 5. This is the rational zeros theorem that we've been using, but I brought it in now as a statement. A statement from a math textbook. Just to show you how difficult it can be to understand it. Volunteer to read? Anyone? Yes, please.
Number 5, right?
5.
The rational zeros theorem. Let f be a polynomial function of degree 1 or higher of the form f of x equals a sub x to the nth power plus a sub n minus 1 x to the n minus 1th power, so on and so forth, plus a to the a sub 1 x plus a sub 0, comma, a sub n cannot equal 0, and a sub 0 cannot equal 0.
And just read that last part there where it says where, and I'll stop you.
Oh, where each coefficient is an integer.
Stop right there. You're at Berkeley now. That's where you're looking now, you're at Berkeley. And they're gonna write polynomial functions, they're not gonna write like this. With numbers. Show you what it works out with numbers, how it looks with numbers, how you can easily do numbers. No, they're gonna start out with, as she read to me, let me find a good marker here, she's this professor. They're saying all these polynomial functions, oh boy, can be written, or the form, I think she started out with, if I'm not mistaken, a subscript n x raised to the n. Oh, okay. Then the second term, that is not strange enough, a subscript n minus 1, x raised to the n minus 1. I don't know whether on the handout they wrote the third term. Did they write the third term or not?
No.
Can someone tell me, what do you think the third term would look like in this standard polynomial function up here?
So n minus 2.
Thank you, n subtract 2, x raised to n minus 2. And it continues like that. A subscript n minus 3, x raised to the n minus 3. So forth and so on, and I heard her read that there should be a term in there that may look like this, a subscript, I think she called it 1x. There might be an x term in there, and then all of a sudden on the end, maybe there's a term that looks like that. And they're saying there are polynomial functions throughout math, grad school and here. They look like that. Now, we identify a few things that are going on here. We're gonna make it easy. Oh, by the way, guys, this one looks like that form. The one I was just discussing here. The a subscript n, right here, is known as the leading coefficient. The first coefficient. A number. It's not there, it's understood to be a 1. This, we all know, represents the degree. Which indicates to me how many zeros to expect. And then other terms, we're most interested in this term on the end. When you finally reach the end, there's no x. So this last term that they have represented as a subscript 0, that's just their representation. Represents that you may have on the end a constant. No x. And in fact, I think I had a constant of a -3. So guys, if I go back, my leading coefficient on the one you see on the board, my leading coefficient is 3. That's going to tell me something. My constant is -3. That's going to tell me something. The 7 is the n. That's the degree, and it tells me something. So it just takes that form for a polynomial function. Now, if that's said, and we'll come back to this handout shortly here. I have, let me see if I can, I do have. Now, we're not finished with the rational zeros here. We know what it looks like. Now conclude.
If P over Q in lowest terms is a rational zero of F, then P must be a factor of A sub 0, and Q must be a factor of A sub n.
There it goes. That P over Q that we've been using in class already. It's called rational zeros theorem. Looks like a ratio, rational, looks like a fraction. She says, to form that fraction, Professor, first list on top, I think she says all the factors of my A subscript 0, my constant. Okay, so on top here, we'll list all the factors of that constant. And Q, I think she mentioned, now list all the factors of my leading coefficient. This one. Didn't we do that before? We've been doing that, haven't we? We used rational zeros theorem, I think, last week. I think we did. Okay, but we may not have known it was that type of a form there. Okay, so it's called rational zeros theorem. Now, with all that said, let me move to part 2. I like to find, and guys, we'll open this up. I like to find the complex zero. You got copies?
Huh?
You got the copies?
Yeah.
You got them there? Oh,
Uh-huh.
oh, you got them back. Thank you. Okay, guys, you goes. I brought one in here. I thought it was interesting. I hope this works out. Oh my goodness, I hope it works out. Here goes. I'm getting scared. Okay. P of X. Why not? Here goes. X to the fifth. Subtract 7x to the fourth. Plus 19x cubed. Subtract 37x squared. Plus 60x. Subtract 36. Make sure that's copied down correctly. First of the guys, how many zeros am I expecting? 5. Now, if you want to go through Descartes' rule and see how many of those 5 could be positive reals, how many could be negative reals, and do that first, it's up to you. Okay? Just out of curiosity, before I jump into it. Descartes' rule, your textbook shows this, so I'm going to discuss it. Guys, kind of the number of variations, let's do it quickly. 1 there, 1 there, oh my goodness, 1 there, 1 there, 1 there. What does that tell me? What does that tell me about those 5 zeros that I'm looking for? All 5 could be positive reals. No negatives, no imaginaries. All 5 could be positive. We'll see what happens. Okay, so possibility is 5 positive. Possibility. Now, these are reals. Now, I heard though when Miriam read this to me, Descartes' rule of signs, she says, Professor, slow down. You also must consider that number, I think, reduced down by 2. I'm using an even number. So what's another possibility? If I take 5, subtract 2, another possibility would be, we may end up with only 3 positive real zeros. And it'll stop there. Can I reduce that down by 2 again? 3 subtract 2, that takes me down to now a possibility of what? 1 positive real zero. Guys, I don't have the zeros yet. I don't know what's going to happen here. Those are the possibilities. That's just for the positive. Now, yes, Oscar.
So I get that it's 5 minus a new integer, and then you do it again. So, okay.
Yes. And I gotta stop at 1. I can't take 1, subtract 2. You're going to negative numbers. That makes no sense here. Number 2. Now let's look at the number of negative real zeros. Descartes says, or you read it to me, she says, Professor, first you gotta find P of a negative X. You're looking for the number of negative possibilities for zeros. That means, because we're going to replace all those x's by negative, guys, I'm going to simplify it fast, if you don't mind. And let's hope I don't make a mistake. Replacing x by negative x cubed. You guys are following me, see if I'm doing this correctly. Please tell me. Is that what that would look like? You go through and replace all the x's with a negative x and simplify it. Anyone follow me? Is that true? How many sign changes do you see here? None. Which tells me there are no what? There are no negative real zeros to worry about here. No negative real zeros. So when I finally take this into consideration, I jump up and start this P over Q business and start checking. Don't check a negative number. You're wasting your time if you try synthetic with a negative number. Descartes says there are none. Okay, here we go. Now by P over Q, that was read to me. Here goes. Rationals zeros theorem and all this business together. Guys, first list all the factors of my constant term, that's what that meant to do. And for a negative 36, quite a few. I'm gonna write mine like this. Here's 1 and 36. 2 and 18. 3 and 12. Oh my goodness. 4 and 9. 6 and 6. I'll write like that. Guys, am I leaving anything out? Are those the factors of a negative 36? What times what will we be a negative 36? Can anyone, I'm not leaving a pair out, am I? Okay, the Q, right here. That should be a factor of my leading coefficient. This out here. Rational zeros here. My leading coefficient in this case is understood, thank goodness, understood to be a 1. Therefore, 7. Now we'll have fun with you. Because you get partial credit for all this. This one problem's going to take 1 page of the test Friday. This will take 1 page. Is that right? Okay. Now, does anyone have, I'm not going to ask you to list all the possibilities, I think we see the possibilities. Does anyone have a possibility when you place one of these numbers over these numbers, you get possibilities? We've already decided no negatives. So I'm looking only for positives. Does anyone see a positive number that you would like for me to check? And I'll do it by synthetic. If it works, we're good. Does anyone have a favorite number?
1.
Oh my goodness, no, 1. There we go. The guys, this is testing. I said that. I heard 1, and 1 would be a possibility. I go back to my polynomial, my coefficients, all of them were these. Just gotta be patient. If I get all this copied down correctly, it looks like that, I think. Okay, let's hope. Here we go. Always start with 0 here, add those up, a 1. Product, 1 times 1 is 1, I get a negative 6. 1 times a negative 6, we did this last week, that's a 13. 13, help me out, I think that's a negative 24. Negative 24, 60 subtract 24 is 36. And 36 here, oh, did we ever luck out? Yes or no? Now, are you gonna be that lucky on Friday? I don't know. I don't know. Somebody may be that lucky that they're out of here in no time. They found their zeros. The rest of us are in here searching for 1. 1 works. Now, if I were you though, I would try this. I don't think it's gonna work here. This thing was, we were expecting on this polynomial 5 zeros. We found 1. So now we're down to 4. So those remaining numbers tell me the coefficients of that, I'll call it a quartic, the remaining polynomial function at this point. I'm going to jot it down just out of curiosity. So that means I have 1x to the 4th, subtract 6x cubed, this is the remaining, 13x squared, subtract 24x, plus 36. Put parentheses around that and show you. That's left over, if you wish to write it out, that's what those numbers mean. That's left over at this point. Now, I was hoping it would leave me something I could just easily factor and find some more zeros. I don't see a way myself. Does anyone see a factoring technique here, grouping or whatever? I don't. But that's what it means. But I just don't see a way to factor it. Sometimes they're easily factored and find the other zeros without additional testing. I don't see that happening here, guys, but I did write down for you, so I need to do additional testing. Now, does anyone have, I get to stack these up, I'm going to test another number, and maybe a student in class has another possibility they think that works. Go for it.
3.
Try 3. Here we go. 3, 0, 1, 3, negative 3, negative 9, 4, 12, negative 12. Look at that. Are you kidding? Descartes says one of these possibilities must work. Guys, right now we have 2 positive real zeros. Oh boy. No negatives. Before I go further, I've got to find the remaining zeros. All 5 positive, I don't think all 5 are going to turn out to be positive. If they do turn out all 5 to be positive, that means, yeah, of course, there's no negatives, and there's no i's. No complex, we call it. If this happens, you get 3 positives, no negatives, and the remaining 2, if this is the case, the remaining 2 are complex. They have i's in them. This one, if I get only 1 positive, and of course there are no negatives, the other 4 are what? Complex. They have i's in them. Okay, let's finish this up. Now, does anyone have, I'm looking for an answer for this one. We could do this. We could test another number. Just stack them up. Or you may say, Professor, let's be clever. Now tell me what these coefficients represent at this point. Now we start out with an x to the 5th. We drop down to an x to the 4th. Do those remaining numbers now in this case represent a cubic? I've already found 2. So this would tell me, I hope it works, that we have 1x cubed, subtract 3x squared, plus 4x, subtract 12 remaining at this point. If that can factor, that would, help us out so much, rather than sitting there and doing additional testing. Does anyone have an idea on the way, what to do to factor this one?
X squared in 4.
Say it again.
X squared in 4.
Oh, more than that, I'll do something else. I got a group. If I group the first 2 and the last 2, being clever, what can I do in the first 2?
Take out X squared.
Take out x squared. Common factor. Leaving x subtract 3. I love grouping when it works. On my last grouping, if it works, I can take out what, 4? And have 4. Look at that. X subtract 3 again. Then now the entire expression, I can pull out what? X subtract 3, leaving what? X squared plus 4. Don't scare me. I heard someone say something else. Is that true, guys? That's a factor? One more holiday, we'll be here until November. Hey, no more holidays. Yes.
You just need the 3 of the multiplication.
Oh, there you go. That's exactly where I'm leading. Hang on to that thought. Hang on to that thought. Now, what you can do, no additional synthetic needed here. With being clever here, writing this out. That means, Professor, I can find the remaining zeros by considering what you have at this point, which is this. Set that equal to 0 and solve it. Well, this is going to give me another 3. This one, if I solve it, let's move that 4 over. Do a square root. I'm expecting 2 answers here. That's a little small quadratic. It's plus minus square root negative 4. Best expressed as plus minus what? No, don't scare me away. Too high. Now, do I finally have all 5 zeros? We were expecting 5, I think, altogether. Do we have 5? Now, when I list them, I'll point something out here. We, by testing, we got 1 first. That's the synthetic. All of a sudden, we get a 3. How many times did that 3 show up? I did my testing, it showed up, and all of a sudden it show up again by the synthetic. Okay, so 3 is repeating, and they call it a multiple answer, multiplicity of 2. Multiplicity of 2, multiple answer. What else did we find? We found some imaginaries, I think, and that was positive 2i and a negative 2i. Do I now have 5 zeros accounted for? Okay, we have the 5 zeros. I'm telling you, if you see one this lengthy, and I write it down on purpose, if you see the one this lengthy, guys, look at this. How lengthy. That's gonna be a workout. That would be a workout. So far, so good? Yes, go ahead.
Can you confirm when we do P over Q, where did we get the Q from, the vector Q?
Where did I get that what now?
We found P over Q,
Uh-huh.
and then the potential numbers for those, where did we get Q from?
Q are the coefficients, the factors of that leading coefficient.
Just the leading coefficient.
Just whatever stuck out front, you list the factors of it on the bottom.
Okay.
So 1 times 1, or -1 times -1.
And for P, it's the factors of.
The constant term on the end.
For P?
P.
Okay. The negative.
Yeah, up here. -36.
Okay.
List all those factors on top of this one.
Mhm.
Now, on the bottom of this rational 0 is 0. You list all the factors of my leading coefficient. Okay? Now, Jonathan, strange things can happen in math. Rational zeros theorem, just like the name rational, you'll never get, in the synthetic, you'll never get a square root. You're not gonna test a square root. So it's not gonna work for irrational. So this works only for rational types. Okay, so you're gonna test and go from there. Now guys, last part of this. First, I had a student tell me, Professor, 3 repeats. Who on earth would think, if I had not done this, look at this guys, I did the red, which I love, saved me from testing more. I'm gonna erase this. We did it by realizing what those numbers represented and factored, and found my zeros. Who on earth would think, unless your instructor warned you ahead of time, go ahead, there's an answer of multiplicity 2. That means one of these that you're testing may work twice. Who on earth would think to test the same number again? Oh, I'm gonna test 3 again, that would be an alternative. So if I test 3 again, look at this guys, 0, 1, 3, 0, 0, 4, 12, 0. Who would want to test a number twice? But sometimes it happens, and it happened here. The 3 is a multiplicity 2, multiple answer, twice. And then of course you can take the remaining numbers here, which names now at this point x squared plus 0x plus 4 is equal to 0, and get, where is it? These two. Now I'm seeing looks all the way, that look after the holiday, that look like, oh no, we're back. Now we'll close this down with this. Look at this. Let me refer you first to the middle school across the street. If that teacher over there gave students this polynomial, it's a trinomial, it's a polynomial. They may not use the vocabulary polynomial over there. And the teacher says, factor this. Well, that's probably, I think. The 2 guys? And they're happy, everyone's happy, it factors. Now, walk back across the street to here, I want to factor this one. factor this one across the street. Now let's come back across. I'm gonna factor this original black function with 1, 2, 3, 4, 5, 6 terms. I wanna factor it. Those kids across the street's not gonna factor that. We are. Now, can anyone get me a start on what the function would look like here, factored? I'll put it right above here. Can you imagine somebody walk up to you and say, factor this? They say factor this, you have no problem. And so we'll get me started? Get me started. Go for it.
X minus one.
Thank you. 1 is an answer, is a 0. Therefore, the factor in your mind that will give you a 1, she's correct. X subtract 1, Professor. You set that equal to 0 on your own, try to solve it, you get 1. Now, help me out with the 3 multiplicity 2.
X minus three, and then another X minus three.
Beautiful. I'll write it like this. Oh, she got it. It's x minus 3, x minus 3. Or x minus 3 squared. We're factoring. Now, I'm asked, it may look awkward. What might the factor look like to get the 2i? What do you think that would look like? Anyway, because we gotta pick up the 2i. What factor?
As squared times four.
X minus? No, I just want one at a time, just this one, then I'll get this one. How about just the 2i? Come on. Yeah, well, I got I got a 2i, x minus 2i, if you're looking at the right one there. That would give me this one. What would give me the last one? X plus 2i. There it is factored. That's nice, isn't it? But it's factored. There it is factored. Done. Now, for the sake of all of us, I may ask you, go ahead and factor like that. That's what I want to see. But also the next step would be, could you please write that factored form, blue, up here. Please rewrite it, and this time don't have an I in your answer. Don't have an I in the factored form. Keep the x subtract 1 that she gave me. Keep the x subtract 3 squared that she gave me. I love that. But for some reason, no, the i's bother me. It's okay to write down, see those i's in there. Does anyone have a method, a way to maybe rid this of those i's? I'll block off the region I'm looking at. How would that simplify? You're gonna saw it at the Warriors Lock session. Tell me what's going on.
I have 2 things.
Go
One,
ahead.
since we already went through the process to finding these zeros, can you just look back at the step before we got our i's and just use that?
You could be clever. But since I didn't do that,
Okay, in that case, you use, the difference of squares.
Okay, look at
A
this.
plus A minus B.
A minus, this next
plus
form is
B.
A minus B and A what? Plus
B.
B. That's what it looks like on the end. Just being clever. Now, middle school says we multiply those two together, out here, that is this. So if you want a quick way to simplify the part that has the i's, and you're trying to rid this thing of those i's, use A squared minus B squared. A is x, so this is x squared. Subtract, and B is what? Is B 2i? B is squared. So it comes down to A squared minus B squared. And if I simplify this further, it's x squared subtract 4i squared. And what's I squared equivalent to? Negative 1. So this becomes x squared, subtract 4 times negative 1, which will give me x squared plus 4. There's no I. Therefore, if I ask for that, now your factored form would be, like I started up there, would be merely on the end, this. No I's. There's factored. Welcome back. Welcome back. I missed you. Or about it. I don't have the time. I don't think. Look at how long that one problem took. I've been known to now ask students to sketch the function. I would like to know what this looks like graphed. Is it a parabola? No. They call it a quintic. It's 5. Degree is 5. That's a graph for it. Now, it may not be a very pretty graph, but I think I will, since I'm doing such a good job in this. Let's get a picture of what the original function looked like to begin with. But before I do that, Farlon, I have a question for you. Descartes' rule says, Ramsey, when you finish this up, one of these should have happened. Now, since I now know the zeros, which happened? We had what? Where am my possibilities here? Where are my zeros? Oh, here are my zeros. Did we get all 5 to be positive? No. Did we get 3 to be positive? We did. We got 1, that's positive, and 3 was acting what? Multiplicity of 2 acting as 0 twice. That's 3. That's 3 positive. So Descartes' rule says expect 3 positive. I got 3 positive. No negatives. I didn't get any negatives up there. Therefore, the other 2 had to be what? From here? Imaginary. And they were. So Descartes' rule tells me that. Now, Barbon, here's comes your question. I want to see what a graph looks like. I'm done with this. Look how time consuming this is, but it makes all kinds of sense, but you gotta work at it. Here we go. And he's gonna help me. Bye-bye. Can you tell the class where on the x-axis, the x-intercepts, where are my x-intercepts if I am attempting to sketch this crazy thing? Where are the x-intercepts?
1 and 3.
1 and 3. Zeros. So we place 1 here, he's exactly right. We'll put 2 here, 3 here. 1 and 3. Can you tell the class where the y-intercept might be?
The y-intercept before 1, that seems the end behavior. I should find it by the end behavior.
How do you find the y-intercept piece? Y-intercept. Yeah, y-intercept merely comes down to this. I see the x-intercept. The y-intercept, p of 0. You go through and replace everything by 0, the x by 0. If I do, all those x terms drop out and leaves me what? Negative 36. So my y-intercept, right, like this, is down here. Place it down here, mark it. The graph is going to go through that point also. So those are my x-intercept, my y-intercept. Now let's discuss the end behavior. I heard you mention end behavior. I got to write down like this. Got down the limit. As x gets large of my function. Now, can someone recall, what does one do when you're considering x is approaching infinity? What do you look at back here, because this is what I'm trying to graph. What do you look at to get an idea what the graph is doing on the ends? What's it depending on?
Power function.
I'll take that, something else. in this particular case here, what should I look at in the black to help me get an idea of what's happening on the ends of this graph I'm attempting to do? It all depends on what? The first term. The complete first term. X to the fifth. Now, I don't know right now, I sort of have an idea what the basic X to the fifth graph looks like. You may know what it looks like. But to answer the end behavior here, it says, as X gets large, you put a large number in here, does it get larger? In your first term, X to the fifth. Therefore, I would assume, since it gets larger, that here this answer is infinity. It's large. On the other end, written like this, limit, as X is approaching negative infinity of my function. You go back to that first term always, and this time you're replacing X by negative. If you raise the negative to the fifth power, you still get a negative.
Yeah.
Okay, and we're putting fairly large numbers in there. So it's a negative infinity. One of my students last week, I forgot who it was, said, Professor, the end behavior, are the answers always infinity or negative infinity? Yes. For us, the end behavior is going to be either an infinity or a negative infinity. Now, out on the right, it says X is approaching positive infinity. Well, the furthest over to the right's here. So this is my end. What should be happening after that? It should be doing that. Out on the other end, negative infinity. Guys, my negative infinity, is that here? Is that the end or is it here? What would you consider the other end at this point to work with? Now this says now go out to the left. And the furthest to the left, is this 0 the furthest to the left I've gone so far? And what should be happening out there? Should it be dropping? So are you telling me maybe it does that? Nope, I see head shaking no. So guys, what are we gonna do? What are we gonna do? I thought the graph would be fairly easy to do, but it looks like I got that one end behavior out of the way. Now I'm concerned about what on earth, Professor, you said out to the left. Is it dropping down like this? I gotta pick up this though, right? Or should I, Oscar, get your, hang on just one second. And also, should I now maybe consider where it touches, where it crosses? We talked about that, that may help you, where it touches, where it crosses. Oscar, go for it.
I was gonna answer your question.
Beautiful. Does that mean that cross and touch?
Yeah.
Beautiful. Okay, I should do cross and touch. At 3, did we discover that 3 had a multiplicity of 2? If it's even, is it true, guys? If it's even, shows up twice here. What should be happening at 3? It should do what? Touch, is that true? And go back up this way, yes or no? Then it's going to come down, so it's got to pick this up. It's going to curve some way up here. Who knows how it's going to curve right now? It's going to curve some way and come down, pick that point up. And by the way, that was 1, and then that 0 showed up only one time. So it's odd, just one time. So it should do what? Cross. So we'll cross that 1. As it crosses 1, should it come on down and pick up my y-intercept? And maybe do that. Yes or no? Ooh. Barbara, you agree? You agree? Look at this. Mr. Park, don't mess up. This is a rough sketch of how this crazy black function looks. Mr. Park, can you put in the original and sketch it, and then I'll ask you, does it look something like we have over there? Would you do that? Can you do that for me?
Sure.
That's a workout. We'll put the original in, have this device to sketch it, and see if it at least takes that shape over there. You might. How many local max do you see on this graph?
Local max.
Local max. How many? I'm not asking you to find it. How many?
In this domain,
Oh, the holiday must have sucked.
just one. Local max.
Right there. That's it. How many local men, I'm not asking you to name it, how many local men do you see?
One.
One, down here. Is there an absolute max on this graph? No, it goes forever. Is there an absolute min on this graph? No, it drops down forever. So that's a pretty good sketch then, with one local max, one local min, and a pretty good sketch of, I can imagine leaving this problem unless you saw, look at this. This mess here, that's his picture. Wow. That's his graph. Miriam, before I close this down, Mr. Parkinson will tell me how close we are. Now, Mr. Parker, I know it may be up higher and lower than we have, but that's okay. Is the shape pretty good?
Yeah, it's really
Wow.
similar.
It's really good?
Yeah, it's really good.
Ooh.
Yeah.
Okay, so that's the shape of that. Miriam,
Mhm.
I don't see on this graph, I don't see anywhere on this graph, where am I? These. And you never will. These are imaginary. They're not on that grid ever. Okay, so they should not be there. Guys, look how much time that took.
There's no way to ever plot them?
Unless you draw an imaginary axis. You may go into a three-dimensional axis. You have an x-axis, y-axis, and a z-axis, they call it. And on that z-axis, you can graph an imaginary. But we're not gonna worry about the z-axis, for goodness sakes. Not at this point. He tells me we're pretty close to the graph here. Okay, guys, take a breath. Chapter 3 is almost over. Whew. I know, it's almost over. Michael, here's what we're gonna do. We're supposed to take a break at what, 4:30? Which I see is coming up soon. Guys, look at this. If I were a student, say, Professor, you're asking me to comprehend all this. And I know we have a knockout exam, and I know you're trying to scare us, but you're saying, oh my goodness, you gotta get ready for this, and this is one you better be scared. You better be scared for this one. You better get ready for this one. Here goes. To close this down, Michael, you will help me out. Let me check and see if this was on your handout. Okay, hold on a second here. Second here. Okay, here we go. This is the way I'm sort of close it down. Michael? Okay, everything started here. Close this down. There it goes. No graphic. No finding zeros. That's it. It is on your handout, but I'm going to just go ahead and jot it down right quick for you. Michael, you gonna help me out? Last part of this is now find a polynomial function. We just abbreviate. That satisfies these conditions. This is a little bit easier, we'll see. I want the degree to be 4. the zeros to be these. A 3, multiple answer, multiplicity of 2, and a -1 for another 0. Negative I. I don't know what polynomial function can you write for me that would satisfy those conditions. No P over Q business. They've already found the zeros for me. So I'd like to know what was the original polynomial? What did it look like? Like mine looked like this. I don't know what this one looks like. Michael, can you give me a start? Just give me a start. What do you think? Not to put you on the spot. What do you think? Yeah, the zeros have already been found for me, thank goodness. They've already found those for me. They want me to go backwards and write the function they came from.
First part can be x minus 3.
X minus 3, got you. Beautiful, beautiful. Hang on now. Love it. Now, do notice it says that 3 was a multiple answer, it should have twice. So I had better do what to ensure that? Thank you. That's done. That takes care of this. He's right. Now, can you give me a nice factor, well, that's not gonna look too nice, but it's there, that would give me a negative I, because they're telling me negative I also is a 0. Does anyone have in mind a factor to give me that?
X squared plus 1.
No, you're ahead of me. Just the negative I. X plus I. And then I know they come in pairs. So if negative I is a 0, automatically positive I is 1. And they call this complex conjugate theorem. I think it's on one of your handouts also. We'll read through that. Therefore, x subtract I is also a 0. They come in pairs, always. Oh, by the way, guys, since I just did this one, did my i's come in pairs even on the one I did? Did we get a 2i and a negative 2i? They come in pairs. Before I get back to this one, suppose you had gotten this, which we didn't. Suppose I had gotten that for one of the zeros. What am I guaranteed by this conjugates? They call it conjugates where you change the sign in between. What else would be a 0 if that one is a 0? 3 what? Minus 4i. They're called complex conjugates. They come in pairs, always. I have it. That's it. Now if I say, please tell me what that looks like, it's a professional problem on this one. This is x squared subtract 6x plus 9. And these two multiply together, I think, if you want to try that a plus b times a minus b, or maybe it's easier to do it some other way. Guys, what we end up with, please help me out here, is it merely x squared minus I squared? Yes or no? On the end. And therefore I got x squared subtract 6x plus 9. Here we go. I squared is equivalent to a -1, so this is x squared subtract a -1. That's I squared. All together, x squared subtract 6x plus 9. Jonathan, before I close and I take a break, I'm going to close your question you asked me at 2 o'clock. This is plus 1. That's p of x. No i's remaining. And actually, I'm supposed to do what? I'm supposed to multiply this out. Aren't I? By the way, I'm not going to expand it all the way out. You're tired by the time you get to this point. Does anyone see what the degree would be? What would be the first term in that expansion if you should multiply it out down here? Is that x to the 4th? And that's what I wanted. I wanted degree 4. Okay, so I'm going to leave it like that. If you want to multiply the thing completely out, go for it. Now though, to close this down. Oh yes, pretty soon. This is on your handout. One more. I'd like to write the polynomial function that does this. The degree is 5. zeros are these. I've got a zero of 1, multiplicity of 3. And also I have a 1 plus I. This is very interesting, take us to the break. And P of 2 has to be equal to -6. Trying to satisfy all 3 conditions. All 3 is 5, not 4. I think I have everything else correct. Okay, guys, I need some help here to close this down. Or should I give you a few seconds to think about it? You want a few seconds just to think about it? Or should we think together? You guys not professor, let's think together. Okay, here we go. Look for P of X. And Jonathan asked the question. I'm gonna approach this much like I did the others. Guys, that 1 multiplicity of 3, anyone tell me what that factor would look like? You get a 1 multiplicity of 3. X minus 1 cubed. That takes care of that. How could I get, I'm gonna be very careful. That's why I brought this in to close down for the break. Does anyone have an idea of how could I write a factor that will give me 1 plus I? And it will look awkward. 1 plus I. Or about.
X squared plus 2x.
Oh, the guy's ahead of me. Just 1 plus I first.
1 minus.
X plus 1 plus I.
Uh-oh, hang on, I don't know what you did. With that in the red, if I ask you to get the X by itself, solve it. In other words, set this equal to 0 and solve it. What'd you get, 1 plus I? This right here. If I say solve this, in other words, set equals 0, move those terms over to get the X by itself, would that take me right to where I wanna go? The sad thing is, they come in pairs. They call them conjugates. So what am I supposed to also consider? It wasn't written for me. What's another 0 automatically up here? 1 minus I. It wasn't written, but it's understood. They come in pairs. They have the I's with them. So 1 plus I, automatically 1 minus I. They're called complex conjugates. Now, if anyone tell me in the blue, a nice factor that would give me the blue one.
X minus 1 plus I.
Thank you. Thank you. You take that blue that he just gave me and say, Professor, I want to solve it. Go for it. So I'll get the X by itself, move 1 over, the I over, takes you right to where I want to go. Now, I've satisfied most of this, yes I have. All right, guys, here we go. Hang on. Without the I's. We've got X minus 1 cubed. I'll do this one, take me right to the break. You guys, well, I break today. Now, I don't know whether anyone can tell me what this mess here, expanded out, will give me, because I'm trying to get rid of the I's. Now, if you want to think of this as grouping, like I did one earlier, and think of this as taking the form of A subtract B, and A plus B, that would definitely give me A squared subtract B squared. That would help me to multiply those two, the red and blue, together. Guys, that would give me, it says square the A, well the A is X minus 1. That's this. Then subtract the B is I. A squared minus B squared. Square the A, subtract and square the B. The B is I. Is that true? I hope if I clean this up, this is X squared, subtract 2X plus 1, subtract I squared, where I squared is equal to a -1. That's gonna make that altogether x squared subtract 2x plus how much? 2. Yes or no? Now my function looks like this. Let's close this down. P of x is equal to x subtract 1 cubed, and without the i's, there's no mistake, we got x squared subtract 2x plus 2. Close it down. Now what am I leaving out? 80? They said don't leave this until you satisfy all the conditions. Another condition was 80.
Yeah.
When I replace x by 2, and what I think the answer is, when I replace x by 2, I'm supposed to get negative 6. If I replace x by 2, 80, 2 subtract 1 cubed is 1. Replacing x by 2. Is it 2? Or, yeah, 2. And here 2, 4 subtract 4, all those drop out, and I get a 2. So guys, what was it all together? 1 times 2, I think I got a 2 altogether. When I replace those x's by 2 and I crunched out, did I get a 2? I think. They wanted what to come out though? Johnson, here goes. They want negative 6. Right now at this point, if I replace the x's by 2, I get 2. No, they want negative 6. I have to modify this answer. Can anyone tell me what you would do to modify 80?
Negative 3.
Place a negative 3 coefficient. Now will I get negative 6? Yes or no, guys? Jonathan? 80, help me out. If, look at this. He says, Professor, the textbook many times will place an A out front. And usually that A is 1, a coefficient of 1. But it could be another number. That's why I brought this one in today. In this case, it looks like it might be a 3. Is that true? At this point, it close down. Another way to think of it. They want a negative 6 to come out. When you replace x by 2, all these x's by 2, we're about to finish up here, guys, now. And the demonstration here. Okay, negative 6, negative 1. When I replace x by 2, this gives me a 1. Down here, I think it's a 2. You got negative 6 is equal to, this is 2a. Divide by 2, that's another way to get 80s. Negative 3 is placed right here. You finish it up. Wow. Now I've satisfied all the conditions. Pretty good, huh? Pretty good. You said, Professor, what else is there? No, what else is there, Professor? I want to get back to 1 plus 1. Really, I want to get back to 1 plus 1. Jeez, where are you going next, Professor? Wait, you wait. See where we're going. Close down chapter 3 after you get a little lengthy break here shortly. They change the functions on us. Not polynomial, like I'm doing now. No, they're saying close down chapter 3 and show students what a rational function, not a rational number, a rational function would look like. And that can be a f. But that's where we'll close it down here shortly. Guys, any concerns here? Anything at all? Okay. I've overworked you today. I've overworked you today. I realize that. I usually give you what, a 15-minute break? Here goes. Now we're not going to the beach. Don't walk over to the beach. Okay, guys, let's say